Okay, I think we'll start. Welcome everybody, wherever you are. Good afternoon, or good morning, or good evening, where in the world you are. So this is the latest webinar in the series of webinars by the IWA Intermittent Water Supply Specialist Group. So today, Joe Dalton's my name. I'm the secretary of the specialist group. So today we have we have multiple speakers, 4 speakers in total from Suez, who are going to present on different projects and tools that Suez are working with on managing intermittent water supply systems. So our first speaker is Satyanaam Bajpai. Sorry if I haven't pronounced your name correctly. And Satyanaam will introduce the next speaker after that, and each of our 4 speakers. Satyanaam is working for Suez on digital tools on managing intermittent water supply projects in India specifically. So Satyanaam, I'll hand over to you.
Thank you, Joel. Thank you so much. Good morning and good afternoon, everyone. First, I would like to thanks to IWA for giving this opportunity to insight on such a critical topic, intermittent water supply system. So I also want to welcome all the participants join us from different region. I am Satyanaam Bajpai. I am leading GIS and digital initiatives for Suez India, particularly in more focus on Coimbatore project. I have over a decade of experience in water services, particularly in GIS and digital activities. And today I will be discussing the real-time monitoring and scheduling in intermittent water supply system. And focusing on practical implementation, challenges, and the impacts what be made in our projects. So before we get into the details, let me give you a quick overview of Suez in India. So we have been supporting cities here for over 40 years, 40 plus years now, and we have built more than 250 drinking water and wastewater treatment plants in India. In municipal water supply and sewerage management services, currently we are operating 9 water management projects covering, serving more than 4 million inhabitants. So we have a contract like Coimbatore, similar to Coimbatore in many cities in India. Like we have 4 cities from Karnataka, which is in southern part of India. Then recently we started Simla project, which is in Himachal Pradesh, and we are also doing one sewage management project in Lucknow, which is in north part of India, under one city, one operator, serving more than 3.5 million inhabitants. So we are there for operation and maintenance of sewer network system and operation and maintenance of the plants as well. So we have a strong footprint in Suez, India. So now let me talk our Coimbatore project. This is one of the most significant project in India, especially in water distribution services project. The project in the right top, we can see the map of Tamil Nadu, which is southern part of India, and then we have a Coimbatore city. Here, our project area is 105 square kilometer, and the project scope include from the study, design, and build water distribution infrastructure, That's include the laying pipes, replacing house service connection, installing meters, constructing elevated service reservoirs, and operation and maintenance, billing, collection, and customer services. So basically, it's a long-term contract. Total duration of the contract is 26 years. The first phase, which was a study period for 1 year, so we have completed successfully in time. This in During this phase, we have basically studied the entire project area, prepare CIP. We call it Capital Investment Plan, which is later approved by the client, and then we move to the next phase called works engineering. So basically,
Sorry, has something gone wrong?
engineering, procurement, and construction, which we are targeting to complete operation and maintenance for the remaining 21 years. Over the operation and maintenance 2019, and since Assia is uh, Assia, am audible?
Yeah, for some time it was interrupted, but now we can hear you. Go ahead.
Okay, great, thank you. So this is so currently we are in the. I was just to quick recap. So I was discussing the project phases of Coimbatore. We are in the second phase now, where we are targeting to complete the works activities by August of this year. Uh, so this is all about quick about the Coimbatore project. If we talk about the current project status, we have made a good progress in project execution. So far, we have completed 94% of the distribution mains. When I say the completion, here I do mean we are in process to replacing the old pipes, which are and laying the new pipes gradually. We have connected more than 1,15,000 of households, uh, and the map here shows our different operational zones. So blue area is basically indicates zones with 24 into 7 water supply, while the lighter sets shows where we work in progress. So we are uh, in efforts to gradually convert this from intermittent to 24/7. That is what the one of objective of this project. So here, like we discussing the challenge in intermittent supply. So when we took over the operation and maintenance of the city of the Coimbatore city in 2019, the we face several key challenges that the system was completely depend on the manual record keeping. So the records were maintained in the hard copy register and notebook. There was no centralized system to track the wall operations, supply timings, and so on. And the field team is also relied on the manual updates, getting instruction from individual authorities through phone, and then they are taking action on these sites. So understanding this all, we realize that there is a need of a structured system for to monitor and analyze the entire distribution system. So to overcome these challenges, we developed the ropes. So ropes is a real-time operation performance system, is which is a Suez India digital initiatives. So this solution basically help us to manage operations and maintenance activities, uh, and the solution drive with the five key principles. We call it collect, assess, publish, act, and integrate. So this is one of the biggest challenge what we can say from our experience in intermittent supply, where the data from the data collection in real time is a challenge. Assessing it, then make it to publish, so that the other concerned authorities can access it, and then the same information can be analyzed for the better decisions. These all the key points are addressed through these ropes digital initiatives. So the wall operations, one of the this is one of our core application. We call it wall operations under the ropes umbrella. It is designed basically for field team to enable real-time data update. We track wall operations and give instant visibility into the supply status through the digital dashboards. So through this application, engineers can choose their respective supply area, and they can send the details, wall operation details, directly from the field. All the essential informations like the supply start time, date, who's the engineer, on what area it is going to supply, what would be the next supply schedule, and so on, can be updated through this application. Application is also having facilities to pop up the notification, to send the notification to the O&M engineers to remind them that as per the schedule, when they have to operate the wall. So we have fixed a program where the engineers get a notification 10 minutes or 5 minutes before uh, to operating wall operation timing. So this is how we are using this application at field to get the uh, essential informations related to the particular area water supply. So here we can see in the right side in the small video, where the engineers are updating the information that what is the area name, what is the supply frequency, the supply is once in a 3 days or 4 days, and then what would be the next supply schedule. So here we can see in this slide that the dashboard is not only giving us the visibility of supply status, but there is also the supply schedules for each pockets. So when users can click on a particular pocket, he or she can see the last supply details, and when the next supply is scheduled, who's the engineer names, what is the mobile number. This all information is captured and available on a fingertip of the O&M engineers. Here, along with the mobile app, we also have a web interface that basically helping us in generating various reports and analyzing supply patterns across different zones. So the users can, our operations team can extract the supply schedule from this application weekly, monthly, and they can plan the maintenance activities. And there are a lot of integration with this supply schedule, which is basically impacting the, and in fact helping to plan the other activities, like if there is any maintenance activities. And then there is a we have, for example, in Coimbatore we have a dedicated water quality sampling team, so they can align their sample collection based on the supply schedules. So there is no I mean, the system is centralized, and they can get the all information on their dashboards. So this is how this application is helping to capture the supply details, and enabling O&M engineers to schedule their next supply, which is accessible to the respective authorities as well as our wall operations team. Then we have this is our screenshot from our digital dashboard. So our integrated dashboard provides real-time visibility into the supply status for both operation team and as well as clients and other authorities in the city. Since its implementation in 2022, so it is live from 2022, it has significantly improved our customer service response because we have a dedicated customer service wing, call centers. They are also having the access on this dashboard, and whenever they are receiving any inquiry related to the supply, they are having information to respond the query uh, more efficiently. And even though it is an intermittent supply, but we can say that it is more informed supply to the customers. So consumers can plan their other activities, and they know that when their next time they are going to receive the water. When we took over the operation and maintenance in the city, there was a challenge because when we interact with the customers door to door to understand their challenges, we came to know that they are not sure that when they are going to get the supply. It is the next day or after 1 days or 2 days or in the evening or morning. So they are ensuring that somebody should be in the house so that when the water is coming, supply is on, they can plan to store the water. Considering that concerns in mind, we have come up with this solution, which is now very much uh, helpful for not only our operations team but more on the to the customers, because they are more informed for the supply. And this data, because we are through these systems, we are basically tracking each and every wall operations in real time, which give us a data to do the analysis, to understand the supply patterns, to identify the area or zones where we have to prioritize few things for improve the supply. Our next presenter, Mr. Sahib, will explain about, will talk about the equitable distributions. So there are a lot of data we are getting to do the more analysis and to plan better. Then there are one more improvement we have done is the integration of AI in the supply scheduling. So now we have a rich data of last 4 years now, 3 to 4 years, which we use to integrate AI to schedule the next supply and to get it validated from the concerned engineers. Okay, so your next supply is in so and so date, and if it is get okay, then that this way we are be more planned, and we can identify where how the systems can be more efficient. So this is how we are managing the I mean, leveraging the digital technology to improve the water services, water management in especially in intermittent water supply. So that's it from my side. Thank you so much. I'm open. I would like to love any. To have any questions.
We'll do questions at the end. If you hand over, I think Shayeeb is the next speaker.
Okay. Yeah. Yeah. Sure. Thank you. Let me make Sahib to host. Yeah. Sahib, can you? I'm not able to see you in the. Okay. Okay. Got it. Yeah. S- so it is Rajia Farmani. That is the name.
No, no, Satyanaam ji. It's my name is there, Shayeeb Ahmed.
Uh, okay. Just a moment. So let me see it. Okay. I can see you. Yes. So now you are the host. Sahib. Thank you.
Okay, yeah. Okay, thank you, Satyanaam ji. Thanks for your nice presentation. I'm just going to share my screen. Just let me know if it is properly shared or not.
Yeah. Sure.
So, is my screen visible? Is it in presentation mode?
Yes.
Fine now. Yeah, carry on.
Yeah. Okay. Thank you. Hello, everyone. My name is Shayeeb Ahmed. I'm associated with Suez since 2017. Uh, I have a global experience of around 15 years, specialized in hydraulic modeling, detailed design of distribution system, transmission main, pressure balancing, water quality modeling, optimization, and now equitable supply. Uh, so to start with, equitable supply is one of the major challenges in all intermittent supply system where the population density is very high and water resources are very less. So hence to overcome this issue, we developed a strategy, a planning uh, to provide equitable water supply. So with this vision, we started our study, which includes both field investigation, hydraulic analysis, and optimization using the tool optimizer. So to begin with the study, we wanted to define out the concept of the study and the objectives. So basically, when we say what is equitable supply, what is the concept of equitable supply? So it is to ensure that everyone has access to an adequate and reliable supply of clean water for their basic needs, regardless of the factors such as socioeconomic status, geographical location, supplying an equal average per capita volume of water to all the pockets or sub DMAs. Basically, when I say pockets, it is a sub DMA within a DMA with sufficient pressure in a scheduled time with available water by identifying and reducing losses in the system. So we have defined our concept. So with this concept, we derived our objectives. So the objectives are of this study are set up equitable water to all the pockets in a DMA, improve supply frequency, enhance the supply duration, avoid inconvenient supply timings, which is basically a night supply. So after defining our concept and the objectives of the study, we move to develop an approach. So basically, we developed two approaches, which is called approach upflow and another one is downflow. So for this particular study, we developed an approach which is called upflow, in which we will do the equitability from reservoir to the pockets by optimizing the intermittent water supply schedule pocket by pocket. Pocket by pocket. So by optimizing the wall operation schedule using optimizer and progressively improving the allocation of extra water by doing loss reduction and eliminating the direct tappings and other privileged supplies. So the one of the major advantages of adopting this approach is there will be no major disturbance in the areas, well-served areas, and we can make a progressive improvement in the other areas. So, moving with this objective and with this approach, we went to hunt for a pilot zone which is called SSH colony in our project area. So as you can see in the screen, the highlighted one is our pilot zone, which is selected. So basically, the criteria for a selection of zone for equitable supply is all the pipe line has been replaced, all the HSE service connection has been given, and the water supply is being supplied in intermittent manner due to uh, low flow availability. So these are some of the features of this pilot zone which has been mentioned here. The area is around 0.76 square kilometer. The population in this area is around 4,528. There are around 804 house service connections. The capacity of the reservoir is 0.3 ml. It has a staging height of 11.7 meters and a storage depth of 4.05 meters. And there are total 9 number of pockets which are being served or sub DMAs from this SR, and there is a sump which is having a capacity of 0.031 ml. So basically for this reservoir currently we are the supply is being provided by pumping, taking the water into the sump, and the depth of the sump is 2.45 meters. So once finalizing our pilot zone and deriving its features, we move to get what are the data requirements and study of each pocket. So here you can see this is the our pilot area where we are showing all the 9 pockets of supply or sub DMAs. So in these sub DMAs, we the data requirements has been captured like asset and operational information, flow measurement at inlet and outlet of the reservoir, flow measurement at each pocket, supply duration of each pocket, and the per capita consumption at each pocket level, and critical pressure points. So we have seen that there are 9 pockets and there are multiple valves which are included in the operation. So if you want to measure the flow in this area, it will be very tedious job since we need to install many flow meters. So to overcome this issue, we identified a certain locations where we can install a minimum number of flow meters, and but we could get the complete data of the entire system. So with that, we installed a flow meter at the tank. We installed at the one flow meter at the inlet of pocket 1, and we found a location to install a flow meter which will give us the data of pocket 2 and pocket 3. And there is one more flow meter installed for pocket 4 to 8 and one flow meter for pocket 22. So by use of these 5 flow meters, we will get a complete flow data of 9 pockets and the SR. And for each pocket we have uh, provided with one pressure point at the highest level, as you can see in my screen with my cursor, that pocket 1, pocket 3, pocket 5, each pocket has been provided with one critical measurement point which is at the peak point of the each pocket. So after defining the all the pockets and installing the flow meters and pressure points, we went to collect more information about the assets and the operations, current operations of the area DMA. So basically in this slide, you can see the information related to all the pockets, the total number of valves, and the diameter of the wall, the material which has been used, and the pipe diameter, and its status of operation, and the frequency of supply, which is mentioned here is once in a 9 days, and the number of rounds for a wall to be operated to open fully, and number of rounds which are being currently operated, and also the supply schedule, start time of the supply for each pocket, start time, and the total number of hours for the supply. So these are our inputs for our study. And one of the observation during this information collection is that the pocket 22 was not able to being supplied by the tank due to its higher elevation and large network. So for this, initially we used to supply the water by tanker because there is very less number of connections. So this is also one of the challenge for us in our study. So moving forward with the asset and operation information, we did a lot of field investigations and field studies where we redefined all the pocket boundaries based on the findings which we had. For example, we did a flow measuring, we did pressure measuring, we did a door-to-door survey during the supply. We did a boundary tightness check and pressure monitoring of adjacent pockets. We did consumer data billing. We calculated the losses, and we did leak detection and rectification activities using visual leak survey and acoustic methods. So in this two images, you can see the difference between the old pockets and new pockets has been shown. So which were modified after the field investigation. As you can see, the pocket 1 old and new, pocket 3, pocket 8, and pocket 7. So these were the pockets which has been modified based on the findings at the site, and it has been redefined. So basically, after redefining these boundaries, we went to establish a baseline for our study, on which we will get we will see the improvisations or results from the optimizer. So to set up a baseline, we did a flow measurement of each pocket. As you can see here, we did pressure measurement for each pocket. So for preparing a baseline, the factors which were considered is the existing supply LPCD, existing supply hours, the supply frequency, the NRW level, and the pressures. So these are the factors which will derive the baseline of the existing system, which will help us to measure our results of post implementation after optimization. So moving forward, after getting all these input details from the site, from the field, we we built our hydraulic model for this particular pilot area. So during hydraulic model building and calibration, we converted all the distribution pockets into the tank elements for the part of calibration. And also we used FCVs in the model to regulate the flow, and we used TCVs to get the supply schedule, supply on and start and stop time. So with this, the calibrated model has been imported into the tool optimizer, and there are many iterations has been done, and many simulations has been done in the optimizer, and the solutions has been developed. So basically in the optimizer, we got the solution in terms of wall operating schedules. So as you can see in on the screen, the X bar shows the time from 0 to 72 hours, which means this is a 3-day supply cycle. And in Y bar, you can see the flow rate. So since the supply was initially, the existing supply was 5 days for this area, but now since it has been reduced to 3 days, so that means we are eventually improved the frequency. So as you can see, the on day one, the optimizer suggests that open the FCV3, that means pocket 3, at morning 6 a.m. Keep the flow rate at 50 m cube per hour and close it by again 11 a.m. So parallelly during this supply, open pocket 22 at morning 8 a.m. Then maintain the 15 m cube per hour flow rate and close it by 11 a.m. Similarly, open pocket 2 at morning 11 a.m. Keep the flow rate around 70 m cube per hour and then close the supply by evening 5 p.m. So like this is with this, the first day of supply will be concluded. Similarly, for the next 2 days, the supply schedule has been provided by optimizer with the desired flow rate and supply timings. However, to maintain this supply schedule, there are certain changes needs to be done at the inlet of the reservoir so that we could not let the tank get overflow, neither get emptied. So for this, we have delivered some solution from the optimizer for the tank operating for the operation of the tanks. So as you can see in the upper graph, as you can see in the upper graph, the wall operation timing of the SR inlet has been given, and in below the profile of the tank filling has been shown. As you can see in day 1, the lowest tank level is the 70%. On day 2, the lowest tank level is 40%, and on day 3 the lowest tank level is around 30%. So this ensures that during our supply there is no case of tank getting overflow, neither nor it is getting emptied. So this will ensure the smooth operations throughout the supply. So with this revised supply schedule, moving to the comparison of the results of the simulation with the existing supply, we see that if you can see the first result of equitable supply which we have gathered, as you can see in the first graph, the green line indicates the existing per capita of each supply pocket, whereas the blue line indicates the optimized LPCD which has came from the optimizer as a result. So when we plotted both together, as you can see, there is a great unequitability was present in the existing supply schedule, in the existing supply pattern. But with the latest revised solution from the optimizer, we could see uh, a flat terrain throughout all the pockets, which means it ensures that the equitable volume of water has been supplied to all the pockets, which is our objective one. And going back to the second slide, you can see that the supply duration has also been significantly improved. As you can see, the blue bar indicates the old supply duration and the green bars indicates the optimized supply duration. As you can see, except pocket 7, rest all the pockets, the supply have hours has been significantly increased or improved by 1 hour or 2 hours, which means that we have increased the supply duration for all the consumers. And moving forward to the third objective, which is improving the supply frequency. So the initial existing supply frequency was once in a 9 days. As you can see here, the SASH tank, which is our pilot area, the existing supply frequency was it would take around 5 days to complete the supply of this tank area, and the adjacent area was being supplied laterally, and then the next cycle was scheduled for this area after 9 days. But with the revised supply schedule, which get concludes only in 3 days instead of 5 days, now we do have a we improved our supply frequency from to 8 days. So this is one of the uh, achievements we could say, or the good results which we have gathered from the optimizer. But however, the next challenge was to implement these results at site. on ground. So for the implementation of these solutions from the optimizer, we developed a proposal. We provided a proposal of new supply schedule by taking the results of the optimizer. As you can see here, day 1, day 2, day 3. So all 3 days, a clear pattern, a clear data of revised supply schedule has been given, which indicates the flow rate to be maintained for each pocket, the supply timings to be maintained for each pocket, and the number of hours to be supplied, and the walls to be operated at which level. So basically for all the 3 days, the supply timing, the flow rate and the duration has been given. And along with this, as you can see, there is a tank operation schedule which has been provided for SR engineers so that they could maintain the tank levels during the supply. You can see for day 1, day 2, day 3, the tank operation schedule, which is morning 6 a.m. to 6 p.m. It has been provided, and the desired flow rate to be maintained at the inlet of the reservoir has also been provided. So this makes the life easy for a SR engineer to for the implementation of these results. However, moving forward, we found that still there could little improvisation can be done in terms of practicality of implementation of these results from the optimizer at site, so that it will have ease for the O&M engineer or the SR engineers at site for the implementation. So to overcome this, we have developed a process flow chart which will help or which will guide the O&M engineer, SR engineer at site for the implementation. As you can see, as a first step in the flow chart, you can see open the inlet valve at morning 6 a.m. and maintain the 55 m³ per hour, which is a rate of flow. Then keep the tank level at morning 80%. Then open the tank outlet 5 rounds out of 33, which is standard we are maintaining at the site right now. Then open the flow meter 2 and pocket 3 inlet valve at morning 6 a.m. and keep it 100% open. Wait for 30 minutes for network filling. This will ensure that since in an intermittent supply, the network gets emptied after completion of the supply. So we are providing 30 minutes of gap so that the network could get filled and it get stable. So once the network gets stable, throttle the FM2 valve till the it reaches 50 m³ per hour, which is the desired flow rate, or we can say the flow rate which has been provided by the optimizer to be maintained. Then open pocket 22 FM4 inlet valve at 8 a.m. Wait for 30 minutes for the stabilization of the network. Once the network is stable, throttle the FM4 valve till the flow rate reaches to 15 m³ per hour. Then close the flow meter of pocket 22 at 10:30. With this, the supply of pocket 22 will be concluded. Then close pocket 3 at 11 a.m., which was opened at morning 6. With this, the supply for pocket 3 gets concluded. Then open pocket 2 inlet at 11 a.m. Wait for 30 minutes again so that the network gets filled and it gets stabilized. Then throttle the FM2 valve till it reaches the 70 m³ per hour flow rate, and then close the FM2 valve at 5 p.m. As you can see, the pocket 2 has been uh, started supply at morning 11 and it is being concluded at 5 p.m. Then close the sump inlet at 6 a.m. So basically you can see with this process flow, it becomes very easy for an operator or an engineer to uh, to implement this revised supply schedule, or we can say the solutions which are derived from the optimizer. So there is no firefighting here. There is no here and there. There is no doubt. So all the process, the complete process has been clearly described here. So similarly, we have the similar kind of process for day 2 and day 3 as well. And as you can see, the objective of avoiding inconvenient supply timing, which is at night, has also been eliminated. As you can see, our supply gets started morning 6 a.m. and it gets concluded at evening 6 p.m. So after implementation of this study at site of the results, now the time comes to check for the results post implementation. So I'll take you to that slide as well. So since after implementation of these new supply schedule for the past 2 months, which is from November 2024 to January 2025, as you can see, we have got the field data from the site. Earlier there were two lines which we were showing you, which is one, the green, which one is the old LPCD which was being supplied, and the blue one which was the LPCD derived from the optimizer solutions, and now the latest yellow one is a field data which is a field outcome. So as you can see, the both the blue line and the yellow lines, which are the optimizer solutions, and the field output is almost similar except for pocket 1 and pocket 4, which is whereas the pocket 4 has got quite higher per capita, whereas the pocket 1 has got little lower per capita. But still, I would say this is a very good results. It's a win-win situation for us, that the results of the optimizer has been almost 90 to 80% accurate, and it is similar to the what has been provided from the tool. But for the one reason why there is a drop in the pocket 1, that is due to the consumers who are present in the pocket 5. They do not have any kind of a storage tanks in their premises as compared to the consumers in the other pockets. So hence, once they take all the water whatever for their basic needs, they will stop the supply, and they will not store any water. So due to this, the flow rate gets decreased, and hence they are having a very low per capita. But except pocket 1, I believe rest all the pockets have performed very well. And in comparison with the old LPCD, which is having very unequitability, it's now quite stable. It's now quite equitable, we can say, because all are having an average around 80 LPCD, which is again a good sign that we have increased our LPCD per capita consumption. So with this, I would like to conclude my presentation. Thank you everyone. Now I will give opportunity to Assia and Olivier to uh, present their presentations on their topic. Thank you. Thank you everyone. Asya, now you are the host.
Hi everyone, can you see my screen?
Yes, we do.
Okay, great. Thanks.
So let's get started. Do you hear me? It's okay?
Yes, we
Yes.
can hear you very well.
Okay. So my name is Olivier Musset. I work for Suez as a operation and maintenance performance manager in Coimbatore for more than 1 year. Let's get started with this question. How to assess, improve, and monitor the performance of the drinking water network? Any manager in charge to operate a potable water service, either under continuous supply or intermittent supply, is facing this question. Suez has developed a solution, a methodology to address this subject using the expertise of 150 experts and also its technical centers. And the tool, which is called WIKTI, has existed over 70 years now, and I will present it to you before Assia comes to the specific case of the intermittent supply. As you can see on the slides, WIKTI stands for Water International Knowledge Transfer Initiative. It has been initially designed for internal purpose to improve the performance of Suez business unit. Then Suez has developed an offer for other water companies around this methodology and its associated tool. This offer has attracted interest and WIKTI has been already deployed worldwide for 70 water companies in 30 countries. WIKTI is a continuous improvement method starting with a self-diagnosis based on which an action plan is defined, implemented, and its progress is monitored. The methodology embraces all the aspects of the performance, the skills, the processes and the organizations, the assets and the investment. WIKTI covers all the business line of the water service, which is described on this slide, operation of the drinking water activity, operation of the wastewater activity, customer services, support processes like HR or health and safety, and cross-functional processes like non-review water that involves both drinking water and customer services. All in all, WIKTI includes an assessment grid for each of the 44 processes of the water management. For each process, an assessment grid is defined around 6 maturity levels. Level 1 corresponds to the basic. Level 3 is referring to the international standard, and level 6 is the excellence level, which means the world-class level. For each level, the assessment is based on between 5 and 15 questions or criteria. All in all, WIKTI includes around 2,600 criteria. Of course, the higher the level is, the more challenges the criteria are. The result of the diagnosis are represented, you can see it on the middle, in the center of the slide, represented in a spider graph, giving a global vision of the maturity of the service for each activity. As you can see on the right side of the slide, which with WIKTI, we also have the possibility to visualize, to target and visualize the objective and to monitor the progress year after year. Now let me talk about the application, about the way we use WIKTI in Coimbatore project. WIKTI has been used last year in 2024 for 2 business lines, customer services and drinking water, but I will speak only about drinking water. For the drinking water activity, we have assessed set processes out of the 10: transport network management, distribution network management, reservoir management, leak detection, electromechanical maintenance, laboratory and water quality control, and water network mapping. 3 processes have not been selected: water resource management and water treatment plant, because it is out of scope of our contract or our project, and works on connection and network because it is not relevant in our project as 90%, 95% of the network and the connection have been already replaced. So it's a very minor activity. The assessments scores show that one process, the water network mapping, which is a GIS, in fact, has reached the international excellence level. Let me point it out that this process is managed by Satyanaam. Two processes are below the standard, which is the level 3, reservoir management and leak detection. And so we have put a maximum of effort to improve these two processes. For each process, except GIS, of course, a detailed action plan has been defined with the concerned manager. And in total, 68 actions have been implemented and already 75% have been completed. Now I let the floor to Assia to present the way a specific module of WIKTI has been developed for the operation of intermittent water supply.
Okay, thank you, Olivier. And hello, everyone. Are you able to hear me now?
Yes, we do.
Okay, great. Thank you. So my name is Assia, and I work at Suez Expertise Center around water distribution network performance management. And as Olivier was saying, the process we'll be talking about today is an adapted WIKTI process for the management of distribution water networks under intermittent water supply. So here, I'll start with more of a contextual slide with the objective of showing the scope of the intermittent water supply regime that we tackle in this process. So in a lot of places around the world, we only know continuous water supply, or what we know as 24/7, with water arriving at our taps at any time of the day. But it's certainly not the case everywhere else. So sometimes you may have a tap, but water is not there all the time. But as we go back to the right, to water, actually access to safe and affordable drinking water is considered by the United Nations as essential to the full exercise of a human being's right to life. Yet up to 2015, more than 663 million people in the world lacked access to what they call improved drinking water, and approximately 2.1 billion people worldwide lacked access to safely managed drinking water. And if we consider the people with access to piped water, so those having piped water on premises, almost half of them is under intermittent water supply. And this phenomenon concerns, if we look at the map, it concerns roughly 1/3 of the population with piped water on premises in both Africa and Latin America, and more than half the population with piped water on premises in Asia. So the scope of this issue means that it can no longer be ignored. And as Jan Dara, so I have this picture here from the first intermittent water supply conference that were organized in Kampala, Uganda. So as she was saying, she was the president of the IWA at the time. It is an undeniable reality. So intermittent water supply is an undeniable reality, and it is high time to take action to improve the situation of the populations concerned. So this is more of a global overview. Now, when it comes to Suez, 8 years ago, approximately, I see that Bambos joined the meeting as well, the webinar as well. So hello, Bambos, and I'm about to talk about you. So we met at Suez with Bambos, who just created the specialist group about intermittent water supply, and we tried to look at the situation from Suez's perspective. So as it turns out, Suez historically had multiple contracts in networks with intermittent water supply. So the map here and the table show some of these historical territories. And as you can see, it's not something that can be easily ignored if we look basically at the mere quantity of it. Another thing is that because we had this important set of contracts, so an important database, we carried out a study of 18 contracts accompanied by interviews with our tenders at Suez, which revealed two key points. So the first one is the fact that the objectives of these contracts are not always adapted to intermittent operation. So here we have two situations. Either classic structures that use the indicators of a contract for a continuous network are modeled on an intermittent network, or the second thing is that an objective of achieving continuity of service is always set as an objective, as a target. The second point is that for all the networks considered, they actually are very poorly described. So the operator finds himself with a network whose characteristics he doesn't know, and the diagnostic phase is necessary. And if contractual deadlines are limited, this becomes very difficult to achieve. So this led us to the importance of tackling networks under intermittent water supply according to their specificities. And here I go to my next slide, where we try to summarize some of the main specificities of these networks. So we tried actually to put them in three main categories: operations, risks, and stakeholders. So when it comes to operation, because the supply is limited in time, more valves are operated for the rationing and the schedule is imposed to the customers. It also entails higher pressure variations because the pipes go from empty to filled states. And because they get empty, the traditional leak detection techniques are not always all possible. The example that comes to mind is acoustic leak detection, which doesn't work when the pipes are not filled with water. When it comes to risks, more frequent valves and pumps operations mean more costs. The filling and emptying cycles can cause damages to the network due to the introduction, for example, of highly pressurized air bubbles that can burst the pipes, which in turn induces more water losses. And because of the pressure variations, negative pressures can be witnessed in these networks, which facilitate the penetration of contaminated substances in the pipe. So it will deteriorate their quality. Finally, and this is very important in the case of intermittent water supply, so contrary to a 24/7 situations, customers are very involved in their interaction with the network. Because the system is quote unquote lacking, they turn to a number of coping strategies to answer their needs. This can go from having, for example, storage tanks or reservoirs at home, or even having domestic treatment systems to counteract the degradation of water quality, or installing booster pumps on the network when the pressure is not enough. And when the supply is still not enough, they might look for water elsewhere. So this is a situation where multiple factors need to be taken into account when dealing with the management of these kinds of network. So starting from this statement, this is what we had in mind when adapting the WIKTI operation and management process for the distribution to intermittent water supply and progressive service improvement. So you must keep in mind that the focus was on service improvement. So transitioning to 24/7 wasn't considered before the higher levels of the WIKTI grid. Another important thing here is the fact that the need was expressed by the operator, namely Suez India, who are with us here today. So the construction of the WIKTI process was very much a collaborative work with the contribution and an important back and forth between Suez India, experts from our expertise centers, other experts who actually were had to deal with intermittent water supply networks all around the world in the networks that were managed at one point by Suez, and the knowledge management team who is in charge of creating and adapting the grid. So once this has been done, the result was a WIKTI assessment grid as per WIKTI process format. So multiple criteria allowing the network to be placed in a number of levels. So as Olivier said, the level 3 and 4 here being the standard at Suez. And if we go for excellence, this is level 6. And for each of these criteria, so we have the assessment grid on one hand, and the other one is that for each of these criteria, a scoring guide would allow the user to mark how well their network answers the statement. So here I just give a first example of a set of criteria that are especially relevant in the case of intermittent water supply management. Here, the example we give is related to leak detection under intermittency. So we go here from the bare minimum, which is a systematic visual leak detection, so a survey on the network, then checking for clear water in sewer systems as well. Then we would have pressurized zone where we could use acoustic methods to detect the leaks, and then go in to use tracer gas techniques for networks that are not even completely filled. The second thing is in relation with the two first presentations. So it's the establishment to the definition and implementation of a supply schedule. So you can see here that when we go from the first to the last level, we gain in details and difficulty. and we have more constraints that are imposed on the criteria. So here we go from first defining the distribution areas. In the case of Coimbatore, this is what Shayeeb called the pockets. So the second thing is the establishment of the schedule, to its anticipation, the communication of the schedule to the customers, to the schedule respecting a number of constraints to allow for an equitable supply to the customers. And the last thing is some technical sheets that were produced. And then we gain in constraints at the very last level. And the very last thing is some technical sheets. So we will have the grid, the scoring guide for each of the criteria, and we will also have a number of documentations, so some technical sheets that actually were produced to accompany the grid and give some more methodological or technical details regarding the standards that were established. So the objective of these sheets is actually to help the operator reach the goals that were established when defining his targets and action plan. And one last thing is the fact that, so let me just click on that. Yeah, great. So these videos show the implementation of the process within the WIKTI application, allowing for a user-friendly experience when assessing the network. So everything, the grid, as well as the scores, as well as the setting of the objectives and the action plan is possible on the application and in a completely digitized manner. And the very last thing I wanted to mention is the fact that the process, so the very new process about intermittent water supply came from India, from Coimbatore in 2024, and it will be normally implemented this year in both Senegal and Angola. And we welcome any candidate networks that would want to try out the process as well. And that's it for me. Maybe I'll give the hosting capability to Joe now.
Fine. Thank you very much, Assia, and all the previous speakers for that variety of information. So we can open up now for discussion and any questions. If anyone wants to ask a question in person, they can feel free to turn on your microphone and ask a question. But we have a few questions in the chat to begin. So one of the first questions was, I think it was mainly, on the first presentation, on Satyanaam's presentation, and specifically the mention of AI, which has been spoken an awful lot about at the moment. It's a question from Nair Ashish. Would like to understand how is AI being used to help determining the water supply schedule in those intermittent supply systems. So yeah, do you want to give any feedback on that issue?
Yeah, sure. So that's a very interesting question. Yes. So basically, the AI is help to predict the next supply. So the prediction is basically integrate the historical supply data. Like I said, we have a rich historical data of last 3 and 4 years. So it's integrate historical supply data with the statistical method along with AI and machine learning. Okay, and I mean the model is just not take into account historical supply alone. It combine multiple factors including patterns, trend, and the supply timing to enhance the adaptability. So this is not because normally we just take the average of the historical data, but AI is help basically integrating AI will be more combination of multiple factors.
Okay. Yeah. What AI tools are these? Are these Suez developed tools, or what are you using? Sort of available AI technologies. What exactly are you using for this?
Yes. So we have our tools what we presented called ropes wall operation, and there we use the AI available AI and machine learning to predict the next supply based on historical data and observations. Yeah.
Okay, thank you. And we have another question as well, also from Nair Ashish. What is the difference in the daily volume supplied to the tank as inflow pre and post intervention in SHS pilot zone? I think that's a question for Shayeeb.
Yes, thank you. Thank you for your question. To give you a simple answer to their question is that in the initial supply of the existing system, the supply was for 5 days for these 9 pockets, but whereas the revised supply schedule which has been provided, that is for the 3 days supply. So hence in that case we cannot make a comparison for the day to day, because it is a comparison of 5 day against 3 days. But in totality we could say in totality, for the complete entire our study area, there is no significant much difference in the inflow volume as compared to the old one and new one. It is remains almost same. But the one thing which we have achieved is the existing NRW level which we have gathered, which was more than 20% earlier, has now been decreased to around 5%. So the savings of water, which is around 15%, has been reallocated to all the consumers. I hope I answered the question.
Yeah, Saeed. So what means with the same water, we are now supplying with better frequency, and we can say the regular frequency and equitable
Yes.
distribution. Absolutely. Yeah.
Yes. Yes. Thank you.
And also an increase NPCD. Yeah?
Yes, exactly.
Okay. Okay, we have another question in the chat to Satyanaam, if you can see that, is from Deary Ba. Is it economically efficient to split DMAs into pockets to make the supply more equitable?
Yes, it is. I mean, the what I understand is from the question is to rezoning the redefining the DMA. So yes, it is possible, subject to the. I mean, yet it's economic. We may need to install few more isolation wall to split the supply zones at site. I mean, it depends the project to project. So I think it is much to study and then come out. Yes,
Okay.
that's what I can say now.
Satyanamji, may I take your question? I,
Yeah,
I,
yeah,
I
please,
hope
please.
it is for me, I guess, but they have
Hmm.
mistakenly quoted it for you. Not an issue. Basically, see, splitting the DMAs into the pockets is not only considered the economical condition, but it is for the ease of operations as well. Because if you are not splitting the DMAs into sub DMAs or supply pockets, it will be very become uneasy for operations team during any kind of maintenance work or breakdown. You need to stop the supply for the entire DMA. If you have pockets which are splitted into small DMAs or sub DMAs, it will be very easy, effective to isolate that particular pocket and keep the supply to rest of the pockets. So it is not only economical in terms of saving time, energy, money, and also it is good from the consumer point of view. So the
Yes,
consumer will not get affected. Thank you.
and in fact the demarcation of DMA or pocket is the output of the hydraulic design. I mean, it's not.
Yeah.
It's all what we want by what we want to improve at site. Yes.
Okay. I was going to ask a follow-up question, Shaib. When you were presenting, yeah, how the pockets are managed, it struck me, it looked like very labor intensive, as in this seemed to be, from what I was reading, interpreting it, this was all in a single day. It's pocket by pocket in a single day. I was going to ask how, when the intermittent supply at a particular area or pocket, would it have water? I mean, I picked up once every 8 or 9 days. It was improved to 8 days, and an average supply 4 to 5 hours per day. So in these pockets, how will be the average supply in these pockets? And if you're, throttling valves, adjusting supply pocket by pocket, like multiple times a day, is it actually an efficient and sustainable way of supplying the water? And yeah, like, you know, given how labor intensive it sounded to me at least.
No, actually, I think there is some miscommunication or maybe misunderstanding. Initially, when we are doing the supply pocket by pocket, right now in intermittent supply, all the distribution system are being using the method of supplying pocket, and now there are multiple operations are involved and with multiple operator. But whereas the in the optimizer, when we put this simulation, we gave us deadline that there will be no multiple operation for one pocket. So for one pocket it is only one open and one close, that's it. So one day one pocket will start and it will close, so that there are no multiple operations for the same pocket as in the traditional old way, but it is limited. For each pocket will have only one opening and one closing time. But since there are the entry points and there is some throttling required, so that we could make a stable flow rate, that's the only thing can be done. And those the entry walls are also at a single place. You no need to go around all the pockets and all the DMA and to throttle the wall. You need to do only throttling at the outlet of the reservoir.
Okay.
So, if I add here that the output of the optimization is also optimizing wall operation. So it
Yes.
is less compared to the previous. However, in your slide, maybe John see so many pockets, so it sounds like more operations. But with the new design of optimized one, basically we reduce the wall operations as well. Yes.
Okay.
Yes, correct.
I want to ask the ropes, that acronym, that was it, real-time operation performance system. Is that a concept or is that a specific software system ye have created? Or is it a
So
concept of multiple systems?
So under yes, so ropes is a is a digital initiatives is a concept, and
Yeah.
under the ropes umbrella we have developed various applications, which basically helping us to make the operation and maintenance more efficient, especially for intermittent water supply. So today I was presented one module called wall operation. Then we have a multiple modules called operation and maintenance. Then we have a CMMS. We have a water quality and so on. So it is a complete package of
Okay.
applications for water services. Yes.
Okay, that's fine. Yeah. We have another question in the chat from Adam Talibi. It's a question for Olivier. When you renewed the house connections in the pockets, what was the rate of the pickpockets, as in illegal connections, that you have found within the renewal plan? Or whoever wants to answer that.
Okay, thank you for this question. In fact, I don't have the answer because I'm not involved in the works activity. But I think it is maybe Satyanaam you have, or Shayeeb you have some information regarding this topic.
Yeah, so in Coimbatore, if we talk specifically, the contract is to renew all the house service connections. When I say we have to replace it and connect with the newly laid pipes. This is one, and second, the in Coimbatore, the more connections are metered from the decades, so there is no such issues came yet on illegal connections. Yeah.
Okay, thank you. I've another question, or more of a comment rather than a question, just on the WIKTI tool. I myself have used the World Bank developed Utility of the Future toolkit, and it seems to me some of the World Bank team, who developed that tool, must have spoken to or maybe even hired former Suez people, because definitely some of the ideas in the WIKTI tool are very similar. I think they must have spoken to you or maybe copied you. I'm not sure, something, but anyway, definitely the maturity assessment, those performance cobweb diagrams, and all that, and the scoring, the assessing from baseline up to world class. That's all there as well. So that's quite interesting to me. But yes, so that's more of a comment than anything. Yeah.
So I have a question for you, Joe. Then, is there a process adapted to intermittent water supply on the World Bank one?
It's not. There isn't a whole thing dedicated to that, but definitely part of the assessment is to assess the continuity of supply. I wouldn't say the whole tool isn't tailored specifically to it. All the latest version of the tool, there is actually a whole NRW assessment which was added to it. I think it's on version 4 now of the tool. But yeah, it's not built specifically for intermittent supply, but any utility can use it. And I myself used it in the Gambia, which is a very much an intermittent supply system. I did, yeah. A question there from Bambos. Are there any indicators, example, cost, capex and opex per extra liters per capita per day supplies or cubic meters per day saved and supplied to the system to demonstrate the financial viability? So yeah, who wants to tackle that question? So.
I think the question is for me, I guess. But as of now, we do not have any extra capex or opex calculated for the extra LPCDs supplied. But we could calculate the savings in terms of the NRW, which will give boost to our revenue collection. So basically, as I told, the NRW in the existing system was earlier more than 20%, which has been now dropped to around 4 to 5% with the revised boundaries. So this is a significant growth, and this will increase our consumer billing data, the revenue. But in terms of OPEX, I don't think so. There is anything related to the OPEX here because the manpower remains same.